Here we would like to discuss computing areas in polar coordinates. So first, let me give you the formula for an area bounded by a polar curve. So suppose you have a polar curve in the plane here. So let this be the polar axis and here is the origin. And you have a polar curve for a certain range of angles theta. Let's say we're looking at the following range for theta. So here are the thetas of interest, and so they are between the angle alpha here, and here is the angle beta. And so this is the range for theta that we're interested in. In this range, we have the curve r equals r of theta. And so this is when theta is between alpha and beta. So the area we're interested in is the following. So let me draw the curve here. So suppose the curve does something like this. And we would like to evaluate the area bounded by the curve. So we are looking at this part here. So this is the area we would like to determine. Okay, so in order to do that, we have the following formula. So first I will give you the formula, and then I will explain to you why this formula is valid. So A is given, the area A is given by the integral from alpha to beta of 1/2 r of theta squared d theta. So to explain to you why this formula works, I want you to think about an element of area in this picture. So let's take this picture again. Put it over here. So the area of interest can be thought of as split into very thin, very long triangles. So this is similar to how we dealt with integration in the case of Cartesian coordinates. In the Cartesian context, what we did there was splitting area into large number of thin, tall rectangles. We're able to compute areas of these thin, tall rectangles precisely, and then we were just adding up these areas. Now, for the polar coordinate system, the elementary, the element of volume consists of pieces like this. So the pieces we have here look like so. Right, so we have a large number of these very thin, very long triangles. So we're basically splitting our area under the curve into a large number of these. Okay. And so now the question is, how do we approximate the area of this rectangle? Right, so what we know about it is the following. So we know that its sides are roughly of length. So these are roughly of length r of theta. So if there's angle theta, say exactly in the middle of between these two rays, right? So if this is theta, then the sides have length roughly r of theta. So we have a very thin, long triangle, like so. This is approximately r of theta. This is also approximately r of theta. We would like to compute the area of this triangle. So you have to recall that area of a triangle is given by the product of its two sides. So if you have two sides in a triangle like this, you can compute its area by taking the product times 1/2 times sine of the angle between them. And so this angle here is delta theta. Let's write d theta for it. Eventually it does become d theta if you take delta theta to 0, and I don't want to write delta theta to prevent confusion with this delta here denoting the triangle. In any way, you have something of this form. So each of these very thin, very long triangles has area given by this expression. And so the idea is we cannot quite integrate this because there is no way we can integrate sine of a differential. So we're not happy with that. So what we do is we say, well, sine is approximately its argument when the argument is very small. So we replace the sine of d theta by d theta proper. And so I can think of this as delta of my area. Okay, so this delta of area, let this be the area of this single triangle. So then I can actually use delta theta for the angle. Okay, so that clarifies the notation. So now I'm writing delta theta for the angle here. Great. And then for the sides, I will just have r of theta squared. And so the reason I can replace sine of delta theta by delta theta itself is very easy. So recall, so to justify this, we have to recall that sine of x is equal to x minus x cubed over 3 plus x, sorry, that's not over 3, that's over 6, or 3 factorial, plus x to the 5th over 5 factorial, and so on. And so when x goes to 0, right, we are effectively truncating these terms, just leaving the first term. So we're saying that sine x is approximately x when x goes to 0, because the subsequent terms are much smaller. When x goes to 0, they are of the higher order, and since x goes to 0, they vanish even faster than x does. And so in here we have the delta A, the increment of this area on the left is given by 1/2 r of theta squared delta theta. And when delta theta goes to 0, when we refine our partition, we get the differential of area is exactly 1/2 r of theta squared d theta. And so that's precisely what we're integrating in this expression over here. So that's effectively the justification for this formula. So what you have to do to justify it is to say, well, I'm going to add up areas of thin rectangles like this, and I will use that sine of an angle is very close to the angle itself when the angle is small. So using this approximation, you're able to replace area of every individual triangle with this expression here, and then that's what you have to integrate in the range of thetas that you have here. Great, so we have justified the formula. So let us further complicate the picture a little bit. Let's say instead of a single curve, instead of an area bounded by a single curve, let's take this picture now. So now we'll have area bounded by two polar curves. So we'll make the picture a bit more involved. So we'll be looking at the area that lives not inside a polar curve, say this one here. So we'll write, we'll say this is r of theta equals f of theta. And then we'll add another curve inside here. And then the area we'll be interested in will live between these two curves. The inner curve will be given by the equation r of theta equals, say, g of theta. So now, how do we determine the red area here? Well, the way to determine the red area would be to compute area bounded by the blue curve using the formula we have over here, and then subtract the formula bounded by the green curve. So what we do is first we compute this entire piece over here, and then we subtract the piece bounded by the green curve over here. And the result of this subtraction gives us precisely the area dashed in red, which we're trying to compute. So this allows us to obtain the following formula. We'll get that area dashed in red here is the integral from alpha to beta, 1/2 f of theta squared minus g of theta squared d theta. So what we did here, we used the formula for the area to evaluate area bounded by the blue curve, and then subtracted area bounded by the green curve and joined these two expressions into a single integral. So now this allows us to evaluate a single integral to find the area bounded by two polar curves.